Okay. So before we start today, I'm not going to do any new material. A couple of things. So we have the test in about, 12 days or so, I believe. And what the test will cover is up to chapter 3. I will start next week systems of particles, but we're not going to see that in the test. So everything you should expect will go up to probably Monday. I'll finish on Monday with some kinetic energy, potential energy, energy in general. So nothing special, but that will be the cutoff for the test. And since I wasn't lying about my code last time, my voice has gone down. What I'll do today, I'll just do an example. Actually, you guys do an example. I want to approach this as this was something you are given on a test, and you have to actually think about it. And you probably have seen it. This is a problem on the book. But I don't care about getting at the end of this. I care about setting up the problem, right? Which, as we discussed at the beginning, is the most important part. I don't care about the implementation as much, because implementation is what an undergrad can do. So I really want to see if we are finally in graduate student mode here, thinking before doing anything, understanding the tools that we studied and understanding how to use them to set up the problem rather than starting to do calculations right away, which is usually a bad idea. So you've seen this probably in the book, and I don't care if you've seen it before. We're going to solve it again. I told you you can solve the same problem thousands of times, and every time you learn something new, and every time you probably do something slightly different, unless you're just copying from the solution manual, which I don't think is a good idea. So it doesn't matter if you've seen it. We see it again. So, and if you have, that's good for you. At least you are reading the book. So there is this circular annulus of radius r. This is its center O. And there is a collar on the annulus that it's moving, can slide on it with viscous friction. And yet, every time we do a problem here, you can go back home and redo it again the same way or change things a little bit. Play with the problems, just test your understanding. So I'm giving you viscous friction in this case. You can go back home and try to do it again with Coulomb friction, for example. I'm not adding gravity. You can add gravity. You can do all these things. There's nothing wrong with that. That's actually a good idea. So this is, we call this point P. The mass of this collar is m, and the radius of the annulus is r. We call this angle theta, and the annulus is given an angular velocity omega, which is constant, about this vertical axis here, if we can call that vertical. I'm not talking about gravity, so it's an abuse of terminology, but let's call that vertical. And so this is the ground, which as usual, it's an inertial reference frame. Radius r, omega is constant, mass is given, viscous friction with constant c that is given too, and I want the differential equation of motion. So I really want to think through the steps. I don't want to get necessarily to the end of this. I don't care. I really want to see if everything we've done has penetrated in your mind and you understanding what you are using, rather than just start attacking the problem right away, which may force you to go back and set it up again multiple times because you haven't thought long enough. And that's why I'm giving you a 24-hour test, because I don't need to rush you in doing this. This is not a competition. This is a more like a dance marathon. This is a marathon. You have to do things many times until you are really ready to do the whole run. So, okay. So I want differential equation of motion. I have a given motion of this annulus here around the vertical axis. And then this is the particle of interest for of course, I want the differential equation of motion for P. That's the only particle with associated mass. So You can tell that the annulus is massless, for example. That's just a guide. Okay, how many? So it's always good to think about where is it that I'm going. If you don't have an idea of the target point in everything that you do, it doesn't make sense that you start moving, right? There's no point at all. So it doesn't make sense that you start writing anything until you know what it is that you're expecting at least. So the first question I have is, you look at these differential equations of motion. That's in general what we say. We say we want the differential equations of motion. But how many do you expect? That's a good thing to ask before you start.
Is it like a ring rotating?
It's a ring rotating, the annulus ring. Yeah, it's a ring that is rotating about the vertical axis. And then there is this mass that can go around it, can slide. It's a collar, I call the collar. So how many equations do you expect? Two? Why do you expect two equations of motion? It's a good exercise. If you don't know how many you expect, why do you start doing stuff? If you don't know if it's 6, 10, 12, 1, none, it could be none. If this theta was locked, well, what's the point of writing equations of motion, right? Why two? Justify why two?
In two directions.
And two directions.
Radial and
There are two rotations. One is given. Omega is given. I give it to you. So how many parameters? Remember what we done at the beginning? We spent weeks in kinematics. Kinematics is deriving velocities and accelerations in terms of given parameters. Those could be Cartesian coordinates, polar coordinates, whatever you want. So if you can describe the motion of a particle, in this case, we're still doing particles here, with a certain number of parameters, you should expect the same number of differential equations, right? So a particle free to move, this is an inertial frame A with this associated coordinate system. A particle P free to move in 3D Euclidean space, how many equations of motion do you expect? How many parameters do you need to represent the position of P in 3D Euclidean space? 3. So in this case, I would expect 3 unless there are constraints, and that's a lot of constraints, right? I do see that the annulus has a given motion, so I am telling you how it is oriented at any given time. So I'll give you probably an orientation at time 0, and then I'll give you the constant angular velocity. So you know how it's oriented. I really just need the position of P along that annulus to tell where P is at all times, because the position of the annulus will be given, the orientation of the annulus will be given. So, and after all, this is what you will see. I told you, imagine that this is what I gave you on the test. You see this drawing here. There must be a reason why I gave you that theta angle there, right? Why would you add more stuff? I don't think you should. And again, do the thinking first. I don't need anything else other than theta. So I really expect one differential equation of motion here, only one. In terms of which variable? Theta. I gave it to you. So, okay, that's the first thing that you need to know. Yes, sure.
I think I saw it in the book too, but
Yeah.
it seems like the thing right there is kind of constrained though.
Which, the collar here?
Yeah, the collar.
Yeah, it can slide. So imagine this is a ring, and then the collar is just another smaller ring that can slide on it, right? And they are in contact, and there is also some friction in this case.
So you think you can't go all the way around the circle?
Well, yeah, I can't go around the circle if this is hinged. I mean, I can imagine that this ring is electromagnetically suspended, and it can float in space. I can rotate. There is no gravity. I can think about anything here. I can have a ring in space. In outer space, there is no gravity, and it's just spinning, and that collar is there, and there is viscous friction. So you can remove this housing if you like. Yeah, or it's fine. You can tell me that it can only go from from 0 to 180. I don't care. That's fine. And then it hits there and it stops. This is just a problem to test our understanding. But you can think about many physical systems where the annulus can probably go. The collar can actually go 360 around that. So. Still doesn't change the fact that I only need theta to tell you where that is, right? Do we agree on this? This is important. You really want to stop and think. So my suggestion is, for everything that you will see in the test, where you actually have to solve a problem, you are facing something like this, a drawing and some requests for you, don't write anything. Think about the where you're going first. Then you do your calculations, reference frames, coordinate systems, etc. But this is important. I expect one differential equation. So if at the end you get more than one, there's something wrong, or maybe they're not independent. So you really have only one. Okay. And then if I want the differential equation of motion, I probably want to use what do I want to use in the end? How do you get differential equations of motion? I'm sorry?
F is good n.
Yeah, and what is that? And that it's an incomplete definition. Yeah, okay. So differential equations of motion come from a particle from Newton's second law, that's what this is called, which tells me that the resultant of all forces acting on the particle P of mass m is equal to mass times the acceleration of the same particle as seen by an observer fixed to the ground. This is something you need to understand. So if you stick in here the acceleration of the particle P with respect to another inertial reference frame, non-inertial reference frame, you cannot do it. That's wrong. So if you write something like this, that is absolutely wrong, because this is a law. This is not even a derived result. So someone observed a long time ago that this is valid, and you're making an abuse if you remove that. I'm sorry, G is inertia in this case. So I think we started calling inertial reference frames N, but N and G are the same thing in this case. So if I'm asking you the differential equation of motion, you start thinking how many you should really have first. Then what do I actually do? What do I use to obtain them? Well, this is one way. We have seen actually angular momentum, and we found differential equation of motion from angular momentum in one problem. Remember the pendulum with the moving attachment point. But that is simply a derived result. The angular momentum expression we found, if you remember, that came from here. We used this expression at some point in the derivation. I defined HQ in N, so this is not a law already, because I defined this vector. It's not something that I observed from nature and I say, okay, that's a law. And this is something I am making up. And so the moment I make something up, it's a definition, it's not a law anymore. And then I took its rate of change and I've used this at some point, and I came up with some different expression that is just an alternative to this. So that could be another way. You can think about if it's worth doing it with angular momentum here. Probably not. And that's not how I'm going to do it. I don't see, like in that problem, a point, an attachment point that is moving. So we said that's very convenient for some types of problems, but not usually. And I would say don't use angular momentum unless I'm telling you to do so, or unless it's obvious that it's an advantage. So I know how many I should expect. I know where I'm going, which is writing this vector equation. So I need these two. Okay, fine. Before we even get this to this, we start thinking about accelerations, and that makes me think about the geometry of motion, which is kinematics. What have we learned in kinematics is reference frames, coordinate systems, transport theorem. Okay. Now, what is happening here? How many rotations do I have? I have two. How many coordinate systems do you think I should have? I'm sorry, reference frames. Three. Okay. Do you want to tell me what they are? So that has wasted already, I don't know, 15 minutes, right? But there is not wasted time. Because if you start doing this, and you don't even know how many equations you should expect, what are you doing? You're just wasting your time if you don't know what are the parameters that uniquely define this problem, and that's theta. That's it. Reference frames. Okay, so definitely I want to say the ground, right? Because it's the inertial one. I can't escape this. I must have an inertial reference frame if someone is asking me equations of motion. Let's define the coordinate system attached to the ground. What do you want to do? And let's justify each choice. Because if you are not able to justify it, it means that you're not understanding dynamics.
Or can I be
O,
yeah, O is not changing.
so this point O is what can I say about O? How do you say it? Right. O is not changing. Yeah. Okay. I'm not changing my position with respect to you guys, but with respect to satellite above me, I am.
It's fixed in ground.
It's fixed with respect to the ground. That's the way to say it. I pick an origin which is fixed with respect to the reference frame that I am looking at, which is the ground for now. It's G. And I'm going to measure things from that point because I have to write F equal MA, where A is seen by an observer fixed to the inertial reference frame. So I really need to be careful in choosing a point which is fixed in the inertial reference frame. Definitely need to do that. OK, now you tell me what basis you want to use. There is no unique and perfect choice. I was going to say solution, but this is not really a solution. This is a choice. You choose the reference frames. You choose the coordinate systems. It's up to you. There is not right or wrong. There is only extremely complicated and non-ideal or something that makes your life easy.
I said T equals 0 and theta equals 90.
OK.
Along OP, yeah.
Along OP. That could be one. So I think I went a little bit ahead of myself here. We're doing the coordinate system. Which other reference frames you want to use? I think we should do that first. So we understand also how to choose the coordinate systems, I think. Which other reference frames you want? We said we want 3, right? So I said that this is 1, and the origin is fine. Let's do the other 2 here. Let's define them, then we do the coordinate systems, because I think it will be easier.
Plane of the ring.
The plane of the ring. So what do you want to call that? A? So plane of ring. OK. And then which other one we use? So that's an obvious reference frame, right? A plane is definitely a set of at least 3 non-collinear points whose mutual distances are constant. I can actually pick 3 for you. 1, 2, and 3. Fine, that's a reference frame. A plane is much more than 3, so that's fine. A particle cannot be a reference frame because it's a point. It's only one. Remember the definition. As I said, here we go back to the basics. The basic things that we have defined and have used several times, but now you think through them. So the ground is one. The plane of the ring is another one. Now we're thinking about the rotation theta, I guess, right? How would you define the last one? You need to define these things. You need to be able to write it down in a way which is not open to any confusions or double meaning. We don't want double meanings here. What do you think?
You could make one fix to the collar and just have a plane that's O, includes O, P, and then just some point that moves along the...
How about the plane? So, right, so plane OP, but that's 2 points, right? So I can probably do, well, that's still a line. 3 points, non-collinear points.
You just have to define a point that's always, that, like OQ, so that OQ is always perpendicular to OP.
What is Q? OP.
So just define
Oh,
OQ,
right.
so that OQ is always perpendicular to OP.
See, this stuff is hard. This is stuff that it's hard to spell out. It's not, I mean, if you don't write it down or think about it or say it out loud, it seems obvious, but then when you have to express it, it's not that obvious. How about a plane perpendicular to the plane A that contains O and P? That's a perfectly legit geometrical definition, right? So it's the D plane, there is only one, the plane perpendicular to A containing what is it? O and P, right? Do we agree with this? I already gave you a plane, which is A. That's a very well-defined plane that contains that object that has at least 3 points, non-collinear, and at fixed distances. And then I can easily define another perpendicular plane, but there are an infinite numbers, but I'm choosing the one that contains O and P at all times so that it is rotating with the vector OP. Make sense? You need to define these things. You can't bypass this stuff. And you need to understand what you're doing. Okay, so now let's go back to the coordinate systems here. We are here, right? What is true about O, by the way? O is fixed in G. Yeah, so I think I'm going to recycle O everywhere, right? Why not? Good. Go back to the ground. And now start looking at the big picture. There are 2 rotations. And I've chosen the reference frames to represent the objects, the rigid bodies, real or imaginary rigid bodies that are rotating with respect to each other. So the first 2 are ground and annulus. And the rotation is that axis there. So between these 2, I really want to define a common basis vector, right? That's what we've done every time. One of the axes of the basis better be aligned with the rotation. You don't have to, but if you don't, you're making your life extremely hard. So I want to start from that one, actually. Ex, I can call it Ex or Ey, whatever there is along omega, right? Why not? Okay. Do you like this? You don't like it because it's called X? I can call it Y. I can call it whatever you want.
I don't know, like, what do you mean along omega?
Well, omega is a vector. I gave you the angular velocity. It's a very well-defined vector in 3D Euclidean space that doesn't care about reference frames and coordinate systems. So it's this thing here. And if I'm giving you this vector in 3D Euclidean space, that's a perfectly well-defined direction in space. You can decide that it has a magnitude and direction. So I can actually, if you want, I can even further define these the following way: omega over its magnitude. That's a perfectly fine Ex, right? It's a vector. I'm giving it to you. So you don't have to worry about that. Okay, so along omega, that's what it means. And then I see the theta going clockwise that way. How about I do EZ into the page? Right? I'm trying to define coordinate systems that see rotations as positive. And again, it's not really required, but that's OK. Now, into page means something very specific here. Yeah, we can say that this is time 0, where we see completely the annulus in front of us. We basically are seeing the, what is the right way to say that? What is time 0? So we're saying here you want to do a time 0. Where the annulus is contained completely in the board. That would be a way, right? That's what really that means. And it doesn't move from there, right? Because this is the ground. It's fixed to the ground. OK, and then EY is, what is EY? C cross with the X, fine. Origin is given. Now I'm looking at the annulus. And I will probably reuse the EX direction. Why not? Because that's the direction of rotation. Now, what do you want to do with this? Now these go with the annulus. This is a fixed coordinate system with the ring, whatever we called it. So I want to say that this is equal to EZ at t equals 0. But then it's not. There is a difference here between these t equals 0. I mean, they are the same vector when the ring is contained into what we've chosen as our reference plane here. So that basically what we're doing here, if you think about it, and this is good thinking. What I'm telling you is that the board is the ground. How about that? All right? The board is the ground. I can do that, right? I see the points here. I see 3 that are fixed at distance. And so this object, this ring, is coming out of the board and then going in and then coming out and then going in. I can do that. So, and that allows me to say into page, or even better, I say into board at t equals 0, where t equals 0, we understand it means the ring is contained into the board completely. So if I look from here, I don't see anything sticking out. Okay? Makes sense. And then this unit vector that is now attached to the ring is big Z only at that instant, every time the ring is contained in the board, but it's not at any other time, because it's going around the ring. Make sense? Okay. EY is same EZ cross with EX. And it's probably a good idea if we start drawing some some planar representations of all these rotations. So it's obvious that we have C friction here. There was viscous friction here. So let's look at these 2 coordinate system and draw something here. So they have, what do we have? Which plane should I look at? Remember, this is very similar to that problem we, lecture 8, that I needed to correct at some point. So let's not make the same mistakes. I'm sorry? XY, right? We sure? It's YZ, right? This is your, the way I chose it at least. This is your big EX, little EX. They are the same, right? Yes.
Wouldn't it be better for A to define one of your directions as like along OP when theta is 90 instead of trying to do into a page at one instant? Because then it would always be true.
That's another way. And actually, I think the way we're defining this has your EY being at theta equal 90 along OP. If you think about it, EX,
Don't you want it to be attached
easy.
to the ring? And if it's along the same direction as EZ?
That is attached to the ring.
For little EZ?
Yeah, it is attached to the ring. It's only equal to big EZ when t equals 0. You don't like it, we can change it. If that doesn't make sense, we can change it. What do you want to do? I'm fine. I mean, this is up to you.
That's okay for you.
I think is this okay with everybody? If it's not okay, we'll change it. We're solving this together. I'm not solving it myself. I mean, I may make some choices here that are not the best ones. So he's saying, and I think it's a good argument. So he's probably saying, okay, this is fine. We're fine with this. And then he's telling us that maybe little EY should be along, what is it, OP at theta equal 90 degrees. That's a good one. And then you choose EZ as the cross product of which ones?
EX and Y.
Are they different? Let's think about this. Are they different? So if this is fine. This is setting up the problem. You may need to do this more than once, as we are doing now. I'm redoing it. I'm just looking at these. Okay, EX is that way, so the way we define EY is like this. Okay? And then is little EZ coming out or going in? And this is going with the ring. This whole So they are actually the same.
It just takes the dependence on time out of it.
But I would rather pick the second one. I would accept both of them, but that's a good point. You really want to start from the common axis, which is the axis of rotation. That would be really nonsense not to reuse big Ex. Then I completely agree that when theta is equal to 90 degrees and you are along OP, that's a very well-defined direction that stays with the ring at all times. And then EZ comes out to be into the page at t equals 0, then goes around with the ring. So, good. Okay. And since I have started this, let's finish it. So, well, yeah, I'm looking at the wrong one. So we were saying I want to see how these two coordinate systems are oriented with respect to each other. They have the same big Ex, big EZ, big Ex, little Ex. So I can start from looking from above, right? These will be the two common vectors. And then what do I see? What is this? Looking from above? EZ probably that way. You want to do it that way? Yeah. EZ is here. And then we have EX. That's EY this way, right? And so the big ones will be the ones fixed to the ground. And then the other two should be, in general, since we're rotating this way, should be these two, right? And I can't really give you an angle because I gave you a constant angular velocity, but I could give you this. Omega t, something like that. Is this making sense? Have we made any mistakes? This is the time to stop and redo it if there are any mistakes, or there may have been better choices for this. I don't see a problem. All agree? All in favor? Move on? Good. So the last one is that plane that contains OP and is perpendicular to the ring at all times. So let's see. I don't want to really erase this. Okay, so now we're doing the last one. And this should be pretty straightforward. What do you want to choose? What do you call these U's maybe? You are along OP. That's it, right? And then maybe, now what is the rotation that is happening here is along this little EZ, right? So I'd better reuse that. And then U theta is UZ cross with UR. Is that right? Let's do that plane. Okay, that plane should be pretty easy here. We have, what was this? Little EY. And then we have little EX, right? So I'm looking from here now. And the little EZ is going in. And it's in common with little UZ. And now I have EUR going this way. U theta going this way. Is that right? Do we agree? You're solving this. I'm executing here. And I'm probably making mistakes. Does it look like for now? Okay. And we have used a lot of time just to do this. But this is where you are showing the understanding of the concepts, because you're setting up the problem. At this point, I have all the ingredients to start computing the acceleration. Well, then we have to model the forces that are here. But this is key.
Do we define theta the right way?
Probably not.
Should
So UR is down that way. Right, good. Paying attention, good. Okay, so this is still little ey that is here contained in the plane of the ring. Ex is going up, but as you just pointed out, little ur, well, it's still there, but this is the angle theta. Correct? Now, where is u theta? U theta is uz crossed with ur. Which way is it? It's going this way. Yes. Okay.
We had it right the first time. We had it right the first time, we just had the theta defined correctly. So
You don't agree with u theta? So if ez is going in, this is ur, and we have uz crossed with ur, and this is, no, I think it should be that way.
so we have z cross r.
It's go. Ez is going inside, right? We said that. We said it's going in, right? This is all fine. There is no rush in checking these things multiple times until we're sure. Yep, makes sense. Any other fixes? Any other issues? Anything we could have done better here? This is where you want to spend time. As I was telling one of you before the class started, setting up the problem is the hard part. Implementing the solution is something MATLAB can do for you, an undergraduate can do for you, but we're not undergraduate students here. We want to invest time in this. The rest is just digging into calculations. Okay. Can we remove all these now? I think we're fine now. We go back to what we wanted, which is f. Want to write this equation, ma of the particle p in g. Okay. Want to start from kinematics. For once, how about we start from f, actually? I can do that, right? They are two different things. I solve one before the other, and then I equate. So this is your particle here of mass m. What am I doing here? Okay, free body diagram. So tell me. Told you there's no gravity, right? There is viscous friction. Go back to concepts, definitions, basic definitions need to be understood and applied correctly. So this is a particle on a surface, right? And we said when we talked about contact forces that those occur in a certain way that we divide into two subsets. What did we call them? Remember when we said, okay, this is a surface, a rigid surface, there is a little particle here that it's moving around, and the forces that they exchange with each other, we said, okay, one component is on the tangent plane at P, and one is perpendicular to the plane. What did I call the one that is tangent to the plane?
The reaction? No, friction. Oh, tangent.
Tangent is friction. So this is the color here that is going on this surface that I can, in first approximation, let's just say it's a curve here, right? It's a line. So if I look at this from our point of view, and we're completely contained in the board in this particular case, what is my tangent plane here? It's this, right? So that is where the friction will be. Okay. And I know it's viscous, so my I already know that my force has at least this term, minus C VREL. It's there. And it must be along this line. Which is this line, by the way? Just defined it. Is U theta, right? This better be along U theta. We'll compute it. We'll see it. But it better be along that line. Yep. And then what about the normal now? What is the normal? Here. You sure?
You are, yes.
Is that the only one we have? Which one? Which one you said? U R N E Z. N E Z, right? Right. So imagine what is really happening here. You have this portion of the curve that is containing this small color here. And so the reaction is going to be, call it R. It's going to be some component on the, what do we call this? The normal direction times UR plus some binormal direction times, which one? Is UZ. Remember what we talked? This is so I'm treating this as a line here. This guide, this ring, it's a line. And so we introduced the intrinsic coordinate. Actually, if you think about it, this is an intrinsic coordinate, probably, very similar. And so why don't we use it? The reaction in general, it's unknown, but in general it can have a component along the radial direction and in this direction. It can, right? Okay, so unfortunately I have to have all that here. Remember, I don't put any minuses unless I really, actually, let's just be consistent. R along R, UR, R along Z, UZ, which I don't know. I don't know them. I may need to compute them. The point here is not really getting to the end of this problem, but in general, that's the way you want to represent forces acting on the particle. Is that all? I think it is. There's no gravity, there's nothing else. So this P is moving on a line. That's how I'm approximating it. I know that tangentially there is this, and my voice is going away. I'm sorry. This friction force. And then the reaction is in general along the other two directions. Okay, let's test another piece of understanding here. What is this? And why don't I write anything here?
Because we derive its constant. If we look at it from any reference frame.
Say that.
It's the same.
Okay, so the relative velocity between, that's how we defined it. When we look at a point on a surface, we define the relative velocity, and that point is in contact with the surface, as the velocity of the particle of mass m with respect to any reference frame minus the velocity of the point as belonging to that surface, I think we called it S, in the same reference frame. And we demonstrated that this is frame independent, so this can be A, G, B, whatever. It doesn't matter. So it's the difference between the velocity of the actual particle of mass m and the velocity at point of contact of the particle P as seen belonging to the surface S in that same reference frame. So what would be a smart way to compute that in this case? Since you can do it in any reference frame here, how would you compute the VREL? which one would you use? A is
Plane of the ring.
the ring, right? Why?
Easier to compute.
Yeah, why? Look at this. So I wrote A, so that happens to be A. Okay, so we use A. A is the ring. It's the whatever we call that plane of the ring, right? Good, we like that. Y, what is S? A. What is this? 0. So let's use the fact that this is frame independent and just do it the easiest way. Okay. So that's the right thinking. Okay, so what is, how do I do that then? What is VRL? It's the velocity of that mass in A. Good. Which is, I'd get you started here. It's definitely the derivative, the rate of change in A of R of the mass, right? Then you tell me what to do. What do you want to do? I don't expect this to be 0, right? It can be at certain times, but it shouldn't be always 0. What do you want to do?
On the position of the particle in the A reference frame. So we can just convert that.
You could.
Use that to convert
You could. Or,
B to A.
so you can write R of M in express these in A, and then you just take your derivatives, or guess what? I'm lazy, I'm going to do this. Plus omega BA cross with RM, which is going to be, okay, RM in B, remember, is the plane that it's going with the particle, and O. So that's 0, because the radius is constant, right? So with respect to that reference frame, I don't see R of M changing. So I'm only left with this omega BAB cross RM, which is, what is omega BA? Which one do you want to use? And what is this? Here you go. And what is the end of the story here? R, U, theta. That's your VREL. Done. You don't have to do crazy calculations. Pick the right reference frame, because this is reference frame free. Don't make your life more complicated. So that took care of this. Then I'm sure you can finish this at home and find the acceleration of that point in the inertial reference frame. And I actually invite you to continue this problem at home. I told you I wasn't going to get to the end, because that's the right amount of time you need to spend in setting up the problem. This was a simulation of a test, really, in my mind. Spend time at the beginning, because once you have all the things figured out, this comes naturally, should come naturally, it shouldn't be a big deal. So finish this and ask me questions via email or office hours if you have any issues. You need to find the acceleration of P in the inertial reference frame and then equate the equation and figure out if you can really remove all these components. My guess is that these UR and UZ, you may be able to ignore them if you write the equations in the right way, and you will end up finding the basically writing the F equal ma only in the U theta direction, so that you get rid of, you don't really care about what these reactions are. That is my guess. But you guys finish it and let me know. Okay? Thanks.